Let's take a look here at the size of sediments that are carried by streams at different velocities. So, the big idea that probably is pretty obvious is that faster moving streams with a higher velocity, carry larger sediment. Just think of a flood. When there's a flood, the water is moving really fast, like in this picture here, and it can carry things like cars and parts of houses in really, really big pieces. But a trickling little brook is not going to carry big pieces. It might carry some little leaves that fell off a tree or some small pebbles. So faster moving water carries larger sediment. That's the big idea. But in our reference table on page 6, we have this chart, relationship of transported particle size to water velocity. This table shows us the relationship of the water velocity required in order to carry different size sediments. So the big bold line here on the graph shows us the relationship between stream velocity and the particle diameter, or the size of the particle that can be carried. Let's quickly take a look at the scale so that we know how to read this graph. On our x-axis here, we have stream velocity, or the speed of the water. And one thing that's really important to notice about this scale is that it is not counting by the same thing in all sections of the graph. This is what we call a logarithmic scale, and we do this on purpose so that all of the data will fit on the page. If we used, let's say, counting by ones, we would never be able to fit all of the data on the page. So we have to count by some different things in different sections of the graph. So let's look at an example. Right here in the middle, you see that this section of the x-axis starts by counting at 1 and it ends at 10. So in this section, this little section, we start at 1 and we count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not true in this section of the graph. Here we start at 10 and we go all the way up to 100. If I tried to count by ones again, 10, 11, 12, 13, 14, it doesn't work. So what's happening here in this section is we're counting by tens, 10, 20, 30, 40, 50. So it's important to know that you're counting by whatever that section of the graph starts with. This is true on our y-axis for particle diameter as well. And let's look at an example. Right here in this section, we start at 1 and we go all the way up to 10. So we're counting by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this section, we'd be counting by tens, 10, 20, 30, all the way up to 100. So in any section of the graph, you are counting by what that section starts with. So now that we understand the scale, let's look at some sample problems. Particle size divisions are important to understand. The dotted lines here on the graph show us where the different particle names start and stop. So if you see these dotted lines, anything in between those dotted lines are that kind of particle. So anything in this section here is considered clay. Here is silt, sand, pebbles, cobbles, and boulders. So you can use either the actual particle diameter on the y-axis scale over here, or you can use the names listed here to describe the particles. So here's a sample problem. What velocity of water is needed to carry a sediment 1 centimeter in diameter? So they're asking us what is the velocity, and they're giving us the information that the sediment is 1 centimeter in diameter. So we're going to start with the information they gave us, 1 centimeter in diameter. We're going to look over until we hit that bold line that shows the relationship, and then we read straight down to velocity, and we see that this is approximately 50 centimeters per second. So the velocity needed to carry a particle 1 centimeter in diameter, 50 centimeters per second. You try. Let's practice another style of question. If the water is moving at 1 centimeter per second, what size particle can it carry? So this is kind of the opposite. They gave us the velocity and they're asking us what size particle. So we're going to start at 1 centimeter per second, that velocity they gave us. read straight up to the bold line, and then over to particle diameter, and we see that we're at about 0.02. So our answer is that 1 centimeter per second water can carry a particle 0.02 centimeters in diameter. You try. Here's the third style of question. If the water is moving at 100 centimeters per second, what particles can it carry? So they're giving us the velocity and they're asking us what particles. So in this case, they don't want to know the actual size, they want to know the particle names. So we start at the velocity they gave us, 100 centimeters per second. We go straight up to that line that shows the relationship, and we read over to the particle names. And we see that we're right here in this pebbles section. But if we think about this, pebbles are a relatively large particle. They're bigger than sand, silt, and clay. So if the river is moving fast enough to carry pebbles, it is also moving fast enough to carry things smaller than pebbles. So this river, moving at 100 centimeters per second, will carry pebbles, but it will also carry sand, silt, and clay. So our answer is all 4. You try. Last style of question. If the water is moving at 1 centimeter per second, what is the largest particle it can carry? So here they give us the stream velocity, and they're asking us what is the largest particle that can be carried. So I want to know what's the biggest thing that this stream will carry. So we start right at the velocity that they gave us, 1 centimeter per second. We go up to that bold line and over to our particle names, and we see that sand is the largest particle that will be carried. So our answer is sand.